Good morning. So we are looking at finding derivatives, and we just learned the general power rule to make our life a little easier when we're looking at the derivative so that we didn't have to use the formal definition. And so we are going to look at the product rule and the quotient rule today and using those rules to take derivatives. So to start out the class, I wanted you guys to try this. And so I just given you guys a few minutes to do that. But if you're watching the recording right now, why don't you pause it and then try watching this, or not try watching this, try taking the derivative of this. And then once you've tried it, then come back on and see if you got it right. So taking the derivative of the first one, right now we don't know the rule, the product rule, but we could expand that out. And so the first thing that you should have done was distributed. And so we can rewrite f of x by distributing the 2x and the minus 3 to the second parentheses 4x squared plus 1. And so if we do that, we get 2x times 4x squared. And so this is 8x cubed. And then distributing the 2x to the positive 1, this gives us plus 2x. We can then distribute our negative 3 to each term. So negative 3 times 4x squared is negative 12x squared. And negative 3 times this positive 1 is negative 3. So just go through and combine like terms. And we get 8x cubed, oops, sorry. Yeah, 8x cubed minus 12x squared. There's no like terms. I'm just going to rewrite it in order. Plus 2x minus 3. So now we can use the derivative and use the general power rule. So general power rule said we're going to take our coefficient in front and multiply it by the power. We're going to bring the power down. So bringing our power down, we have 3 all times x, and then we're going to subtract 1 from our power. Minus, and then keep our 12 there, times our exponent, which is 2, and then x, and subtract 1 from our exponent. So 2 minus 1. Plus, so we have that 2 there, bring our power down, which is 1. And if we subtract 1 from that exponent, we have x to the 1 minus 1 power. And then the derivative of a constant is 0. So simplifying it, we have 8 times 3, so that's 24. X to the 3 minus 1 power, so x squared, minus 12 times 2, which is 24, x, and then plus 2, x to the 0 power is just 1. So we don't have to write that. Okay, so we get that derivative was 24x squared minus 24x plus 2. You guys get it? Or if you didn't, do you see where you went wrong and what you needed to do?
Yes, thank you.
Okay. And then the second one, we can use the quotient rule. Well, we don't know that yet. And so now, but we can rewrite this using rules of exponents and rewriting this to break it down so that we can use our general power rule. So notice that our denominator, the square root of x here, so let me just rewrite it, y equals 7x to the 4th minus 2x squared, all over the square root of x. Square root of x, let's at this point just rewrite it as x to the 1/2 power. Because we only have one term here in this denominator, we can break this up as 2 separate fractions. So we have y is equal to the first term, 7x to the 4th, all over our denominator, x to the 1/2. And then our other fraction is minus 2x squared in the numerator all over x to the 1/2. So now we're going to use the rules of exponents that say if you're dividing same base here, we can subtract the exponent. So we have 7x to the exponent of 4 minus the exponent in the denominator of 1/2. And then same idea for the second fraction. So we have minus 2x squared, and then we're going to subtract the exponent from the bottom, minus 1/2. So in order to combine terms that have fractions in there, we need a common denominator. And so 4 minus 1/2, our common denominator is 2. So we need to get 2 in the denominator for 4. So we have y is equal to 7, x to the 8/2 minus 1/2. So 8/2 minus 1/2 is 7/2. Minus 2x to the, so this is 4/2 minus 1/2, which is 3/2. So now it's in the form that we can use that general power rule and we can take the derivative. So dy dx was just another way to say take the derivative of y, and it's just telling us that dx is that we have a variable is x. Okay, so same idea, bring our power down front. So 7 times that power, 7/2, x to the 7/2 minus 1. So whenever I'm subtracting 1 and my exponent here is a fraction, it's just easier to write that 1 with a common denominator. So minus 2/2. Minus 2x to the 3/2. Oops, sorry, didn't bring down my power. So multiply the negative 2 times our power here of 3/2. And then x to the 3/2. I'm going to subtract 1, but again, that's a fraction, common denominator. So let's rewrite that 1 as 2/2. So dy over dx is equal to, so rules with multiplication of fractions. There's nothing to simplify, so let's just multiply straight across in the numerator and denominator. So 7 times 7 is 49 all over 1 times 2, which is 2. So we have 49/2, x to the, well, 7/2 minus 2/2 is 5/2. Minus, well, in this fraction here, we have negative 2 times 3/2, but the 2's can cancel. And so we're really left with negative 3. X to the, well, 3/2 minus 2/2 is 1/2. So we can leave it like that, or we can rewrite it in radical form. But those are not like terms, and so we're not going to be able to add those together. So hopefully you were able to get that, or again, if you got caught up, you found out where you got caught up, and that now makes sense. Okay, so that brings us to 2 new rules so that, you know, we could go about it this way, or we can use our new rules, the product rule and the quotient rule. And so the product rule. So let's start out with using the formal definition of derivatives to derive that product rule. So let's say that you have a y is equal to f of x times g of x. And f of x and g of x are both differentiable. Then the derivative of y, so we can say dy dx, I'm just going to give you the derivative first, is equal to f prime of x, the derivative of the first, times the second function g of x, plus the first function f of x times the derivative of the second g prime of x. Okay, so for product rule, we can't just take the derivative of the first function times the derivative of the second function. It doesn't work. And so that is the rule to take the product. If you have two functions, you take the derivative of the first times the second plus the first times the derivative of the second. You might see this in a different order, but commutative property holds in the case if you see it in that order. So let's show that that's what we actually get if we take the derivative. So if y is equal to f of x times g of x, dy dx is equal to the limit as h approaches 0 of f of x plus h times our second function g of x plus h minus the original, so f of x times g of x all over h. So the problem is if we plug in 0 wherever we see an x, we're going to get the form 0 over 0, which doesn't tell us anything. So there is a trick here. Excuse me. So a lot of times we like to manipulate our expression or what we're working with so that things will fall out. So we are going to add a funky 0. And so that funky 0 that we're going to have, so we have this limit, we have to bring this down still. As h goes to 0 of our original, or this f of x plus h, g of x plus h, and this is where we're going to add in that value. So let's do f of x plus h times g of x. Okay, so I need to add 0 in here. So if I'm subtracting that off, then I'm going to need to add it. So plus f of x plus h times g of x. So that's just adding 0. So it doesn't change it. Let's bring this down, or it's equivalent. So minus f of x all times g of x. And this is all over our h value. So let's break this down into two separate fractions. And so we're going to look at the limit as h goes to 0 of this first grouping. And notice that first grouping, and look at what they both have in common there. They both have this f of x plus h in here. So when we write this first fraction, let's pull out that f of x plus h from both of those terms. So if you pull this f of x plus h out of f of x plus h times g of x plus h, you're left with the g of x plus h. And if you pull out that f of x plus h from this minus f of x plus h times g of x, you're just left with a minus g of x. And this is all over this h. And then we have the second grouping. The second grouping here, notice that you have this f of x plus h times g of x minus f of x times g of x. So let's again look at what those two have in common there. And so notice both of those terms have a g of x in common. So we're going to do that same sort of idea there. We're going to pull out what they have in common. And so we're going to pull out the g of x. I need a plus. And I'm pulling out g of x from both of those terms. And so if I pull out of g of x from f of x plus h times g of x, you're just left with that f of x plus h term. And then I have this minus. Well, if we pull out g of x from f of x times g of x, you're just left with that f of x term. Close off that bracket. And we have to put that all over h. We're going to use our rules of limits. So we found that if we limit of a sum of functions, we can look at the limit of the first function plus the limit of the second function. So let's rewrite that with two separate limits. And at the same time, let's pull what we had done out front. So we have the limit here. We pulled out this f of x plus h. Remember the limit, also going to use a rule here of limits with a product of two functions. So a limit of a product of two functions is the same thing as a limit of the first function times the limit of the second function. So we're going to do that too. So let's just do that here. So times the limit h goes to 0 of this piece in here. So this is g of x plus h minus g of x all over h. So the limit of the second function and that second fraction, we're going to do the same thing. So we're going to look at the limit of the piece that we pulled out, g of x. So limit as h goes to 0 of g of x times the limit as h goes to 0 of that second piece. Which was f of x plus h minus f of x all over h. Well, this should look familiar to you. The limit as h goes to 0 of g of x plus h minus g of x all over h. Also, this piece should also look really familiar to you. The limit of f of x plus h minus f of x all over h. That's just the definition. That's the definition of a derivative, right? So we can just rewrite this piece as g prime of x if we wanted. And this is just the formal definition of the derivative of f of x. So let's just write that piece as f prime of x. Okay, so if we look at the limit as h goes to 0 of this f of x plus h, well, that's saying go in, plug in 0 wherever you see an h in here. So if we go in and we plug in a 0 wherever we see an h, here we're just left with the f of x out front. And then we have this plus. Well, again, we need to look at this limit here as h goes to 0 of g of x. Notice there's no h in this function. And so because there's no h in this function, this is just going to give us back g of x. And so this is what we got the derivative to be. So we found dy dx is equal to the following. The first function times the derivative of the second plus the second function times the derivative of the first. And let me just show you the one I gave you. Dy dx is equal to f prime of x all times g of x plus f of x times g prime of x. So notice, if you add 2 plus 3, you can change the sum. It's 3 plus 2. So basically, this piece right here, I write first. Oh, no, I don't. I write that second. I'm going the wrong way. This is mine. And then this one, if you multiplication, so I'm moving this one first, but multiplication, 2 times 3 is the same thing as 3 times 2. Again, your commutative property. So I just had the order changed there. But they mean the exact same thing. And it might be helpful when we look at the quotient rule to think derivative of the first times the second. So we can apply this to find the derivative if we have a product of two things, two different functions. And so notice, let's look at that one example or an example similar with, it doesn't have to be the one we did today, but something similar to that. So if we had f of x is equal to 5x squared minus 6x plus 1 all times 2x plus 5. So use the product rule to find f prime of x. If it helps you, we could call this a different function because I used f of x up there. So what this tells us is we're going to take the derivative of our first function. So derivative of this first function. So we can use that general power rule. So we have the 5 times, bring our power down front, x, subtract 1 from our power, so 2 minus 1, minus 6 times 1, plus the derivative of 1 is 0. So it says take that derivative times the second, 2x plus 5, plus the first function, 5x squared minus 6x plus 1, times the derivative of the second. So if I take the derivative of the second, that gives me just 2. So we have 10x minus 6 all time 2x plus 5 plus, and we can distribute here. So this gives us 10x squared minus 12x plus 2. Distribute. So we can clean it up. So we have 10x times 2x, that's 20x squared. We have 10x times 5, so that's 50x, so plus 50x. So negative 6 times 2x, so minus 12x. And negative 6 times 5 is minus 30. Let's bring down everything else. So plus 10x squared minus 12x plus 2. Combine like terms. So 10x plus 20x, sorry, 20x squared plus 10x squared is 30x squared. 50x minus 12x is 38x. 38x minus 12x is 26x. And that will be plus 26x. One more. So negative 30 plus 2, so that's negative 28. So in that case, I don't know how much faster that would have been is. Instead of expanding that and just taking the derivative first. So same idea. So let's just show it because I think it's a much faster in this case if we just distribute. So find f prime of x by first distributing. Before you take the derivative. Okay, so we got f of x in this case is 5x squared minus 6x plus 1. And we're going to distribute to 2x plus 5. To distribute 5x squared to each term, we get 5x squared times 2x is 10x cubed. 5x squared times 5, so that's plus 25x squared. Distribute the negative 6. So negative 6 times 2x, that is negative 12x. And negative 6x times 5 is negative 30x. And then distribute 1. So 1 times 2x is plus 2x. And 1 times 5 is plus 5. Combine like terms. So we just have a 10x cubed, a 25x squared, so that's 25x squared. I missed a square somewhere. Yeah, this should have been minus 12x squared. So it really was 25x squared minus 12x squared. So that is plus 13x squared. And then we have negative 30x plus 2x. So that's minus 28x plus 5. So now take the derivative using the general power rule. So bring down our power down front, multiply it to that coefficient, 10. So 10 times 3 is 30. Subtract 1 from our power, so now it's a square. Plus, so we're going to have 13 times our exponent of 2. So 13 times 2 is 26. X, subtract 1 from our exponent is just 1. Minus, derivative of x is 1 times that negative 28, so just minus 28. And the derivative of this constant 5 is 0. Okay, so exact same thing that we got above. And one may be or might not be easier than the other. But unless it tells you what way to do it, do the method that you feel most comfortable. There's going to be times where we cannot, maybe not be able to do that and distribute. Pull another one. So we're given that q of x is equal to x to the negative 2 power minus x to the negative 3 power, all times 3x to the negative 1 plus 4x to the negative 4. And so find the derivative of q of x. So let's just use a product rule. So the derivative of the first parentheses, so the derivative of x to the negative 2 power, bring our power down front. So that's a negative 2x, and subtract 1 from our power. So negative 2 minus 1 is negative 3. General power rule for the second term in that first parentheses. So bring the negative 3 down front. So we have minus 1 times negative 3. So this is really plus 3. X to the, subtract 1 from our exponent. Negative 3 minus 1 is negative 4. All times the second parentheses. So let's just rewrite it. 3x to the negative 1 plus 4x to the negative 4. Plus the first piece, first parentheses, which is x minus 2 minus x to the negative 3rd times the derivative of the second. So derivative of the second, bring our power down front, negative 1 times the coefficient of 3 in front. So that's negative 3x. Subtract 1 from our exponent, negative 1 minus 1 is negative 2. Derivative of the next term in the second parentheses, bring our negative 4 down front, times that coefficient of 4. So negative 4 times 4, so minus 16x, and subtract 1 from the exponent of negative 4, we get negative 5. They actually have it expanded, and so we got to use rules of exponents, just that when we're multiplying same base, you add your exponents. And so q prime of x is equal to, so negative 2x to the negative 3rd times 3x to the negative 1. So negative 2 times 3 is negative 6. X to the negative 3rd times x to the negative 1, add our exponents, x to the negative 4. Negative 2x to the negative 3 times the next term, 4x to the negative 4. So negative 2 times 4 is negative 8. X, negative 3 plus negative 4 gives us negative 7. Distributing the second term, 3x to the negative 4 times 3x to the negative 1, that gives us plus 9x to the negative 5. 3x to the negative 4 times 4x to the negative 4, 3 times 4, so that's 12x. Add our exponents, negative 4 minus 4 is negative 8. Okay, so we just distributed those first two parentheses, plus now I'll do the same thing with distributing those last two parentheses. So x to the negative 2 times negative 3x to the negative 2. I actually get a negative, so I'm going to minus 3x, add our exponents. Negative 2 minus 2 is negative 4. X to the negative 2 times negative 16, x to the negative 5, so that's minus 16x. Add the exponents. Negative 2 minus 5 is negative 7. Distribute the negative x to the negative 3 to the negative 3x to the negative 2. So negative times negative is positive, so that's plus 3. X to the negative 3, x to the negative 2. Add the exponents. Negative 3 minus 2 is negative 5. Last one, negative x to the negative 3 times negative 16, x to the negative 5, that's a plus 16. And negative 3 minus 5 is negative 8, so x to the negative 8. Just curious what way they went. So they did go in descending order of powers. So because these are negatives, our highest power, the largest exponent, is x to the negative 4th power. So look at this and see if there are any other terms with x to the negative 4th, which there is. And so we're going to sum those two. So negative 6 x to the negative 4th minus 3x to the negative 4th. So that gives us negative 9x to the negative 4th. So next highest would be that 9x to the negative 5 plus 3x to the negative 5. So 9 plus 3, so this is plus 12x to the negative 5. I don't see any 6 powers. And there's not. So 7. So we have negative 8x to the negative 7 minus 16x to the negative 7. So that is negative 16 minus 8 minus 24x to the negative 7. And then 12x to the negative 8 plus 16x to the negative 8, that's plus 28x to the negative 8. Okay, so a lot of this is algebra and distributing and using rules and simplifying. So that's the product rule. Let's jump into the quotient rule real quick. So it would be nice, but it's not true, that if you have two functions, so let's call it maybe y is equal to some function f of x all over some function g of x. And both f of x and g of x are differentiable. Just want my pen bigger. Now I had to get really small to get everything in there. So I'm just going to do this. Okay, so we have y is equal to some function f of x all over some function g of x. We're given that they're both differentiable. We have to say that g of x can't equal 0. Then the derivative, dy dx of y, is equal to the derivative of the first, or the top, f of x, times the bottom, g of x, minus the top, f of x, times the derivative of the denominator, g of x, all over taking your function g of x in the denominator and squaring this whole thing. So I don't think I'm going to go through and prove it, but we could. But let's use it. And I don't remember what I had before, but something similar to what we did was, let's say y was equal to 4x minus 3 all over the square root of x. So here was that case where we split it up at the beginning of class as two separate fractions. We used our rules of exponents, and then we took the derivative. But now with that quotient rule, we can use that. And let me just rewrite this a little bit before we use that quotient rule. So y is equal to 4x minus 3. Rewrite your radical in exponential form. So this is x to the 1/2 power. So order matters here. And so you have to take the derivative of the numerator first. And so the derivative of our numerator, well, that's not too bad, 4x minus 3. So the derivative of our numerator, so y prime equals, derivative of 4x is just 4. And the derivative of our -3, derivative of a constant, is just 0. So it's the derivative of our numerator, which we just took, times our denominator. So I can put it as x to the 1/2 or square root x. I'm not taking the derivative, let's just put square root of x. Minus the first function, which is 4x minus 3. Excuse me, my allergies, I believe. 4x minus 3. All times the derivative of our denominator. So the derivative of our denominator, oops, let's use this piece. Bring our power down front, 1/2 x, and subtract 1 from our power. So subtracting 1 from 1/2. So 1/2, I'm just going to write it right now, minus 2/2. All over our denominator, which was the square root of x. And then it tells us to square that piece. Okay, so y prime is equal to 4 square root of x minus, let's pull this 1/2 out front. 1/2 doesn't really matter. X to the 1/2 minus 2/2. X to the 1/2 minus 2/2 is x to the -1/2. All times this 4x minus 3. And that is, well, if you square a square root, you're just left with what's underneath the square root, which is x. Notice that we can distribute this x to the -1/2. Well, actually, we can distribute this whole -1/2, x to the 1/2 to each term inside. So let's just bring down our 4 square roots of x minus, well, 1/2 times 4, that's just 2. X to the -1/2 plus, or times, but we're adding our exponent. So x to the -1/2 times x. So -1/2 power plus 1. -1/2 plus 2/2, so that's 1/2. And then -1/2, x to the -1/2 times -3, so this is plus 3/2. X to the -1/2. All over x. Just curious how far they take it. Okay, so we want to clean this up some more. And there's a couple ways that we can clean this up some more. We can, because it's a single term here in the denominator, we can rewrite it as 3 separate fractions, and we can use our rules of exponents. Or we can rewrite this as a single fraction, but right now we have fractions within fractions, which we don't like. So I think it might be easiest if we just break this down. So this would be really 4 square root of x, but I'm going to write that as x to the 1/2 power at this moment, all over this x. Minus 2, I have x to the 1/2 power, all over this x. Plus 3/2, x to the negative 1/2 power, all over x. So 4x, subtract exponents. So 1/2 minus this exponent of 1. So 1/2 minus 2/2 is negative 1/2. Minus 2, so 1/2 minus 1. Oops, is that multiplication there? No. I guess I could combine things. I guess I'll do it later. X to the negative 1/2. And this is plus 3/2. Negative 1/2 minus 1. So negative 1/2 minus 2/2 is negative 3/2. So that's the negative 3/2. These are like terms. They have the same variable raised to the exact same exponent, so we can combine those. 4 minus 2 is 2. X to the negative 1/2 plus 3/2. X to the negative 3/2. So there, technically, I think that was a lot harder to use that quotient rule. And that was another case that we could have manipulated it and rewritten it before we took the derivative. Should we take a break before we do one more? Does that sound good? Okay. So we're looking at more examples of using quotient and product rule. And so looking at this example, f of x equals the quantity 3x squared plus 1 times the quantity 2x minus 1. And that is all over the quantity 5x plus 4. So I noticed that I'm going to have to use, in the form that it's written right now, I'm going to have to use the quotient rule. And within that quotient rule, when I take the derivative of the numerator, I have to use the product rule. It looks like it would be really messy to me, and I think it would be much easier if we first distribute that numerator. So let's just go ahead and do that. So if we distribute the numerator, we have 3x squared plus 2x, so that's 6x cubed. We have 3x squared minus 1, so that's minus 3x squared. We have 1 times 2x, so that's plus 2x. And 1 times negative 1 gives us minus 1. All over our denominator 5x plus 4. So there's no like terms in that numerator. And so now let's take the derivative. So quotient rule, derivative of the top. So I'm going to actually rewrite this. I'm not going to take the derivative right now. I'm just going to put in the rule. So this is saying d dx means I'm taking the derivative of this piece, 6x cubed minus 3x squared plus 2x minus 1 times the bottom, which is 5x plus 4, minus the derivative of the bottom, so d dx of this 5x plus 4 all times the numerator. So the numerator, that was the 6x cubed minus 3x squared plus 2x minus 1 all over that denominator, 5x plus 4. That quantity has to be squared. So taking the derivative of the numerator, derivative of 6x cubed, so that's 18x squared, minus the derivative of 3x squared is 6x, plus the derivative of 2x is 2, all times the denominator, 5x plus 4. Minus, so the derivative of the denominator, derivative of 5x is just 5. Derivative of the constant is 0. So we just have that 5 there for that derivative times the numerator, 6x cubed minus 3x squared plus 2x minus 1. All over the denominator, 5x plus 4 quantity squared. So we're going to clean it up by distributing, combining like terms in the numerator. So 18x squared times 5x, 18 times 5, that's 40, that's 90. So that's 90x cubed. 18x squared times 4, 18 times 4, so 8 times 4, that's 32, carry my 3, that's going to be 72 x squared. And then distribute my negative 6x, so negative 6x times 5x is negative 30x squared. Negative 6x times positive 4, that's negative 24x. And then distribute the 2. 2 times 5x, that's 10x. And 2 times this 4 gives us plus 8. At the same time, let's now distribute the negative 5. So distributing negative 5, you get negative 5 times 6x cubed, so that's negative 30x cubed. Negative 5 times negative 3x squared, that's 5x squared. No, that's 15x squared. Negative 5 times 2x, that's negative 10x. And negative 5 times negative 1 is plus 5. And that is all over that denominator squared. So combining like terms, 90x cubed minus 30x cubed is 60x cubed. I have a 72x squared plus a 15, so that's going to be 85, so plus 85x squared. Oops, I see another square. Minus 30x squared. So 55 minus 30, so that would, I'm sorry, 85 minus 30 is 55, so that'd be positive 55.
Excuse me, where did you get the 85? 72 and 15 is 87.
72 plus 15, 87. Okay, yep, you're right, 87. And then 87 minus 30 is 57. There we go. And then we have for our just single x, we have negative 24x plus 14x. I'm sorry, I'm doing it in my head and then I'm saying it. So negative 24x plus 10x is negative 14x, and negative 14x minus 10x is negative 24x. Okay, and the last one is 8 plus 5, so that's plus 13. All over our denominator, 5x plus 4, quantity squared. I lost it. I don't know where it jumped to. Okay, so that was our f prime of x. Okay, so you're given information about functions and them evaluated at particular values. So g of 3 you're given is 4. You're given that g prime of 3, excuse me, is equal to 5. F of 3 is equal to 9. And f prime of 3 is equal to 8. And we're going to find h prime of 3. So derivative of h evaluated at 3. We're given that h of x is equal to f of x times g of x. Okay, so we want to use the product rule to find h prime of x. So product rule says h prime of x is equal to the derivative of the first. So we're going to write it as f prime of x times the second, g of x, plus the first, f of x, times the derivative of the second, g prime of x. I don't like that. Well, then it told us to find, we really want to find what h prime of 3 is. So we're going to go in here, and wherever we see an x, we're going to replace it with a 3. And so that says, well, find f prime of 3 times g of 3 plus f of 3 times g prime of 3. But we were given that information above. So our f prime of 3, this one was equal to 8 times g of 3. G of 3 here was equal to 4 plus f of 3. F of 3 here was given to us as 9 times g prime of 3. And g prime of 3 was 5. So we have 8 times 4 is 32, plus 9 times 5 is 45. 32 plus 45 is 77. So if you ever see something that says average cost, function, how we denote it is with a bar over that cost function, C of X. And how we find this is we take our cost function, C of X, and we divide it by X. So same sort of idea, average revenue function. We denote it with a bar over the revenue R of X. And this is equal to just what your revenue function was, and divide that by X. And similarly, the average profit. P of X, the bar over it, this is your profit function, whatever they gave you, all divided by X. So we might want the rate of change of the average cost, or the rate of change of the average revenue, or rate of change of average profit. And that is called the marginal. So if you ever see the marginal in front of it, it's telling you to take the derivative. So marginal average cost and we're going to look at the derivative of our average cost function. So notice we have some function divided by X. So when we're taking these marginal average cost, or marginal profit, or marginal revenue, we're going to have to use the quotient rule. I should put average in there. Okay, so let's look at a problem. So it states, a company that manufactures bicycles has determined that a new employee can assemble MD bicycles per day. Actually, this is not one of those average. We'll come back to that one. Let's look at this one. So average profit. The total profit in tens of dollars from selling X self-help books is the following. P of X is given as 5x minus 6 all over 2x plus 3. And the average profit from each sales level. And then it says find the marginal average profit. And then is this reasonable function for profit? Why or why not? And so this is profit in tens of dollars. And and this is from selling. X self-help books, or X books. For A, find the average cost. Sorry, not average cost, average profit. We're in profit. From each sales level. So if it says 8 books, okay, so this is our average profit. So it's already given us that function. All we have to do here is go in and plug in what X is. So in our case, X is equal to 8 here. And so if we look at P of 8, we're just going to go in wherever we see an X, and our profit function, we're going to plug in 8. So 5 times 8 minus 6, that is all over 2 times 8 plus 3. So 5 times 8 is 40. 40 minus 6 is 34. 2 times 8 is 16. 16 plus 3 is 19. Is that right? No. Okay, so 34 divided by 19 is 1.78. But that's a profit or average profit from each sales level. Let's look at the profit at 7 books. So if we go in here and we plug that in, 5 times 7 minus 6 all over 2 times 7 plus 3. So this gives us 35 minus 6 is 29. 2 times 7 is 14 plus 3, that's 17. And 29 divided by 17 gives us 1.7. Shoot, something's off. One more, let's look at 10. No, actually I want 9. So if I go in here and I plug in 9 wherever I see an X, I get 45 minus 6. 45 minus 6 is 39. And 2 times 9, so that's 18 plus 3, so that's 21. 39 divided by 21. Okay, so something, I'm realizing something's off. Let's just pause for a sec. Okay, so I figured out what was wrong. This was my profit function and not my average profit. So if I want to look at my average profit, and we were just talking about that, I have to divide that function by x. So let's just go over here. Let's look at p of x again. P of x here was equal to 5x minus 6 all over 2x plus 3. And if I take this function and I divide it all by x, this is what my average profit is. Okay, well, that's the same thing as saying 5x minus 6 all over 2x plus 3. Another way to write this, divided by x. Division fractions. Take your first fraction, 5x minus 6 all over 2x plus 3, and multiply it by the reciprocal. That's just 1 over x. So let's just distribute this x down here in the denominator. And so if we distribute this x down here in our denominator, we get 5x minus 6 all over 2x squared plus 3x. Technically, all I have to do is divide our answer by x, or in our case, here, if I wanted this, to bar over this would have been this 1.78 all divided by 8. Okay. This gives me I get 22 or 0.223. But this is per 10, x is equal to 10. So this is times 10, x is equal to, this is 10 tens of dollars. I had rounded wrong. It was 0.2236. And so this is going to be a 4. So $2.24 per book is the average cost of 8 books. So we can do the same thing with those other numbers. We can divide by that and get what that average cost is per book. But let's skip to this piece, which says find the marginal average profit function. Find the marginal average profit function. So we found the average profit. And that was our original, that was the 5x minus 6 all over 2x squared plus 3x. So we need to find the derivative of this. So we need to use the quotient rule. So derivative of the numerator, derivative of 5x is just 5, derivative of negative 6 is 0. So derivative of the numerator is just 5 times the denominator, 2x squared plus 3x, minus the numerator, which is 5x minus 6, times the derivative of the denominator. So derivative of 2x squared, bring the power down front, we get 4x. And then derivative of 3x, we get plus 3. All over this quantity squared. So 2x squared plus 3x quantity squared. So let's distribute the 5. We get 10x squared plus 15x minus, we got to be careful here because that negative is going to need to distribute later. So let's put a bracket. So 5x times 4x is 20x squared. 5x times 3, so that's plus 15x. Distribute the negative 6, I get negative 24x minus 18. All over the denominator, quantity squared. So we need to distribute that negative. So basically it's going to change every single sign inside that bracket. So let's just combine while we are at it. So we have a 10x squared and we're going to have a negative 20x squared. So that's going to be a 10x squared minus 20x squared is negative 10x squared. Here, distributing my negative, I have a negative 15x plus a 24x. That's going to be 9x, so plus 9x. And here, this is going to be a positive 18 plus this 15. So that's 33 plus 33. All over the denominator, quantity squared. This is the marginal average cost function. Okay, so that was on the quotient and the product rule, using those. And the next rule in here has to do with another rule that's going to be really helpful when we take the derivative, which is called the chain rule. Something that will be helpful for you once we start the chain rule is if you guys remember how to use and work with composition of functions. So good review.
No, wait, because you stopped.
Composition, two functions.
No. Stop.
Okay, so that's something to look at, and we might look at a couple, but basically that's saying if you have two functions, f of g of x, that's one way to say it. One way to write it is f little circle g of x.
Yeah.
So you're basically taking a function, g of x, and you're plugging it in wherever you see an x and f of x. You guys have already kind of been doing that. We can think of x plus h as a function. You're plugging that in wherever you see an x and f of x. So kind of thinking, we've already kind of done it, if we want to think of it that way. Okay, so that's to come on Wednesday, looking at using the chain rule to find derivatives, and then also quickly kind of reviewing a little chapter 3, because you guys are going to have a test on chapter 3 on my math lab over the weekend. Stop.